Alright, let's get started. Hello everyone. Today we're going to be talking about this problem. It's been a while, but we're going to be starting off with this graph problem. So let's read the question and see and try to figure out exactly what it's asking for. Given an undirected graph, count the number of connected components. So here's an example. Let's say we have n is equal to 5. So n is the number of nodes labeled from 0 to n minus 1. So you're given the number of nodes in the graph, right? And you want to see how many of those nodes are connected. So we see here that 0 is connected to 1, 1 is connected to 2, and 3 is connected to 4. So those are the nodes that are connected. Now, what we're trying to see is that the output is 2 here. And the reason the output is 2 is because we have to basically see that, okay, 0 is connected to 1, that is one connection there, 1 is connected to 2, that's another connection there, but then 3 is connected to 4, and that's like a completely separate connection to everything else. So like 0 is connected to 1, 1 is connected to 2, and then those two are connected. However, 3 and 4 are completely separate. So you see how those two are part of the connected nodes, 1 and 2 are, but 3 and 4 are completely separate. So yeah, so those are the two separate connections. 3 and 4 is a connection, and 0, 1, 2 are a connection. So those are the connected components, basically. So, how would we go about solving this problem? So we see that like we want to basically start from like a root and then continuously traverse to the graph to see where the connection ends, and then once we find another component, like a potential component, we have to increment that, so we need to add that somewhere else. So a way we can do this is, first of all, we need to figure out what the best way to represent this graph is. Would it be an adjacency matrix, an adjacency list, whatever, and then we have to do some sort of traversal through the graph. So let's get started. Let's say we're going to say def count components, and then we'll say the number. So we need to take n as the number of nodes as an input, and edges. So the edges are going to be the type of like basically the array of components that we put in. So this is going to be in the form of a list in a list, basically a 2D array. So we have that as our function. So now how would we go about doing this? I think to start off with, we need to create the type of representation that we're going to be putting for this graph, and I think the best way to do that would be to make an adjacency list. So how do we make that adjacency list? Well, let's call the variable that we're doing graph, and as you guys might know, an adjacency list is basically in the form of a dictionary where you have like some certain edge, let's say it's 1, and then it's connected to every single sorry about that. Um, I'll worry about this another time. Just that'll just okay. So then we have like a node, and that's connected to every single other node. All right. So now, how would we represent this node? So we know that there's n nodes, and then we have to have like some type of way for each node to be connected. So what we're going to do here is that we're going to have each individual node with a connection connected to a list which will contain all its neighbors. So for example, in this graph, 0, it's only connected to 1, so there would only be the input of 0 connected to 1 in this list. But if there was another connection, let's say like there was something like 0 comma 4, there like was a connection between 0 and 4, here would be 1, and 4, because those are the two neighbors it's connected to. But how would we represent this? How would we go about making the graph in the first place? We could do this trick for the dictionary. We could say for I in range of n. So basically what this will do is essentially it'll make the list for every single node, and it'll have a blank list to start off with for every single one of its neighbors. So this is the empty graph that we're going to be starting off with in the adjacency list form. And to build this, what we want to do is we're going to have two variables to basically append every single node and the value in the edges into this graph, basically, right? So we have edges which are going to be 0, 1. So we have two elements in each of the edges list. So what we're going to do is we're going to increment them by 0, u comma v. So we're going to have u comma v representing the first and the 0th and the first index in each of the lists in edges. And what we're going to do is we're just basically just going to append them to the list. So we're going to say graph of, not the parentheses, bracket of u, so the first element, we know that there's a connection to the first one, so when we are inputting 0, we want 1 to be in the list. Graph of u dot append, and we're going to append v, and it's going to go the other way around. So if there's a connection from 0 to 1, there's got to be a connection from 1 to 0. So we'll also append a graph of v dot append u. Alright, so that's how we would start off with just creating our adjacency list. Next, we need to find a way to actually go about traversing this list to find out all the connected components, right? So basically, what we're going to be doing is we're going to be making a visited list, because we want to see in most types of traversal methods, we want to see how many nodes we visited so far and keep track of them. So what we're going to be doing is, typically it's done using a set, because it's a convenient small data structure that we can use efficiently to store basically the edges and nodes that we visit. And now what we want to do is we want to create a depth first search method. Obviously this could work with either a breadth first search method or a depth first search method, but for now we're going to start with a depth first search method to basically traverse through the graph and see all the connected components that'll line up to make each component. So let's go dfs in this thing, and then what do we need? We just need the node. Sorry. So we take a node as an input, and we're going to be doing basically going to be traversing through the thing. And as you guys might remember from a while back, a depth first search is a type of first in last out method. So it's going to be a stack based method where the first node that you input in is the one that gets outputted last, and you continuously traverse through the list by basically removing the most recent node once you add it to the stack. So we're going to be creating a stack essentially. So we're going to start out with it being a stack, with it basically being a list, because a list you can basically pop out the last node. We're going to be starting with the first node that we just inputted into this depth first search. And now to traverse this, we're going to say while stack, basically while this list is not empty. When the list is empty, we can basically return out, because that's it. Cur is equal to stack.pop. So this is where we're keeping track of the most recent element. Stack.pop means we're just basically taking out the last node. And then what do we do here? What we want to do basically is we want to essentially see, we have this visited set, right? What we want to see is if this if the node we're looking for is in the visited list, and if it is, you can if it isn't, basically we basically just want to add the thing that we have. So let's say for what variable should we call this? For new node, in graph of current. Basically, what this means is, remember here, each node we have has a list of the neighbors that's in the adjacency list that we created up here. We are going to say we're basically looping through the neighbors. If new node is not in visited, so we can just say not in visited to quickly check. This is an n complexity solution, not an n complexity solution, I mean an n complexity action. We'll basically say we're going to add the new node. And we're also going to append that to the stack. So this is how we keep the stack going, basically. So this is how we basically perform a depth first search, continuously checking in each of the neighbors, checking if it's in the visited list, and if it isn't, we just add it in. And basically that's how we get this visited list that we're going to be using later. Next, that's the depth first search done. Now we can say we want to keep track of what is called the components. This is the thing we want to return, right? Components. We'll start it out as 0, obviously. And now what we want to do is we want to use that visited list to see whether or not the thing that we're keeping track of is part of a new component or if it's the part of the old component. And this is how we're going to be using the visited set. So now we'll say for node in range of n. Basically, we're going to be keeping track of every single node in the adjacency list that we created here. And what we're going to say is that if the node is not in the visited list, then we know that it's going to be a new component. So what do we do? Because if the node was part of the visited set already, that means that we're just part of the same component, so we don't need to do anything. But if it's not, if node not in visited, then all we need to do is add visited.add node, and then we're going to basically not exactly recursively, well, kind of recursively, but we're going to be performing the depth first search function that we created on that node. So we're not just doing this on the first node, we're going to be doing it on every single subsequent node as well. So every node and each of its neighbors, we're going to be continuously running the depth first search function that we just created. And then finally, here's the key part. We also know that since it's not in the visited node, we can simply increment the components amount by 1. Alright. And that's basically it. We can return components. And yeah, that should be it. Let's save the code here. And let's give it a shot, how we can basically test out this code to see whether we got everything right. So let's run count components. Let's print it out first, since we want to print out count components. I did put this in the right place, yeah. And what we want to input into count components, let's take our example, ignoring this one, of course. What we want to see is that if we input these things and the number 5, so 5 comma this thing, what we should end up with is, since there's these five nodes, 0, 1, 2, 3, and 4, we can see that 0, 1, 2 this is all one component, this is another component, so those should be 2 separate components there. So the output should be 2 if we did everything right, and I hope I did. And there we go, we see that we get exactly 2 components. For example, we can also check if we add another connection, like let's say we connect 2 to 3, that means that it's going to be one component, because you see 2 and 3 are connected, so it's just all going to be one big component. So let's see if that works. And yes, when we run the code, we get a 1 because this is all just one component. And we can keep testing with various different test cases. You guys are can feel free to try this out on your own. One final thing is what is the time complexity of this program. So we had to build this graph in the first place. That is going to be a time complexity of n, probably, depending on how much nodes that we had in the graph, for example. So usually we'd call it probably something like E, like the number of nodes represented by E. And then we also have to perform a depth first search over this entire on each thing. And if you guys remember, a depth first search complexity, it goes from one node to another to another to another, and that is also a time complexity of n. However, these two are counted as two separate time complexities, so that would be a total complexity. Let's call the complexity of building the graph E, and the performing the depth first search over all the nodes as V. The total time complexity would be something called like, oops, sorry, doing that. The total complexity would be a time complexity of V plus E, and the space complexity is actually also the exact same thing, because it takes exactly that much space to create a graph and as much space in the stack memory to run the depth first search. So that's also going to be V plus E. So there it is. That's how you solve this problem with the given time complexity, and hopefully you guys got a better understanding on how to perform a depth first search traversal to solve this kind of problem on a graph, and also the building of the adjacency list and everything like that. So hopefully you guys learned a thing or two, and I'll see you guys next time. See ya.